Okay, hello people watching this video. We are on the step paper that has the example of hypothesis testing. We're going to finish and we're going to go through the rest of these steps. We've done all the heavy lifting so far. Now we just have to find a conclusion, okay? So I'm going to run through kind of the stuff that we've been talking about. The company, the Mars Candy Company, is claiming 24% blue, right? But we did a sample of 100 M&Ms and we got 27% blue. So we're saying, okay, are they wrong to advertise 24%? Can they get away with advertising 24% if we actually got 27? Are those close enough to being the same thing that we're like, okay, you're all right? Like, you know, that cutoff, is it within the range? Okay, so what we did is we come up with a null and alternative hypothesis. Your null hypothesis, I said yesterday, will always be equal. You'll always have an equal sign on your null hypothesis. So it's equal to whatever they're claiming. Equal to whatever they're claiming. And then your alternative hypothesis will usually be not equal to. Sometimes you'll have less than and sometimes you'll have greater than. We'll talk about those later on. But that's kind of how that works, yeah? Okay, next, we went through and we calculated our test statistic, which we have the formulas for. That was what you guys did for homework, right? You calculated all those formulas depending on whether you're doing a proportion, a mean, or a standard deviation. This one was a proportion and we got 0.702. That was our Z value, right? And normally I said Z value is between -3 and 3. So 0.702 is fine, right? We're within one standard deviation, okay? Now here's the deal. I'm going to do this two different ways, and you have to learn both ways because sometimes it's easier to do one versus the other. There is a p-value method, and then there's a critical value method, okay? I like the critical value method, but for some reason last year when I taught this, like the majority of everybody else liked the p-value method. So I'm going to show you both, and you can decide which one you like, but you have to know both. Okay, so here's the deal. The critical value method, we said that Z has to be 1.96 for a 95% or a 0.05 confidence level. We got that from the chart, right? 1.96. Do you guys remember that number as being like a commonly used number, 1.96, okay? 0.05 is 1.96. All right, so here's how the critical value method works.
Are you recording?
Yes, I am. Here's how the critical value method works. So bump over here onto this side. I'm going to draw out a bell curve. Always draw out a bell curve, regardless of whether you're doing p-value or critical value method. Here we go. 0 still lives in the middle, right? And then what we have to decide is whether 27% is an extreme value, right? In comparison to 24%. So 27% does live over here in comparison to 24%, right? Okay? So we chunk off that one and we chunk off this one, right? And what I do is I color them black. And I say if it's in the black, it's bad. Because if it's in the black, that means it's an extreme value. Does that make sense? If it's in the shaded range, it's considered to be far enough away from 24% that we deem it to be a bad percentage, right? Like 30% might be too far away from 24%. We have to decide where the 27 lives, okay? This cutoff mark right here for a Z is 1.96. This determines, and technically on the back side it will be negative 1.96. That is the Z-score that I use to determine whether it's considered to be an extreme value or not, right? Okay, so again, keep in mind that my 24% has a Z-score of 0, right? Like that's the scale that we convert it to. 24% is a score of 0, right? 27% has a Z-score of what? What's the Z-score for my 27%? 24% is the middle number, yep. 0.702, right? That's the Z-score that I have there. Okay, where does the 0.702 live? Like somewhere over here, right? Like between 0 and 1.96. This is where my 27% lives. Oop, 27%. Because he has a Z-score of 0.702, right? So is he considered to be an extreme value? No.
Is extreme in the shaded area?
Extreme is the shaded region, yes. Extreme, the shaded region is the bad region. That's considered to be a shaded region. So we can conclude that even though we got 27%, are they okay with saying it's 24% instead?
Yeah.
Yeah, because 27 is close enough to 24%. If we would have gotten a number with a z-score that's over in this range, we're like, oh, that's too high. They need to revise their 24% and say something different. Does that make sense? Okay. So here's how this works when we do our conclusion. We are saying the 0.702 or the 27% lives in that region. Okay. So let's make a decision. If it's in this shaded region, I'll write out a key code for you. If shaded, if in shaded region, we reject the null hypothesis. That's always what you do. If it's in the shaded region, it is bad and we reject the null hypothesis. So let's talk about what the null hypothesis is. We said from up above, I'm going to rewrite it, that our H naught was that P was equal to 0.24, and our alternative hypothesis was that P was not equal to 0.24, right? Okay, so if it's in the shaded region, we reject the null hypothesis. So if we would get a number over here, we would say, nope, you're wrong. It's not equal to 0.24. But hold on, don't write that, because we didn't get it in the shaded region, right? If it's in the shaded region, we say you're wrong. It's not equal to 0.24. But since we got a number that is within the limits, right? It's not considered to be an extreme value. We go ahead and say, okay, maybe that's correct, right? Maybe it is equal to 0.24. Maybe it's close enough to 0.24 to say 0.24 is okay, right? So here is what we say. We're not rejecting the null hypothesis, but we're technically not accepting it either. This is the tricky part. We're not rejecting it, but we're not accepting it either. Here's the deal. If you fail to reject, you just write fail to reject. This is the conclusion that we're going to come up with. Fail to reject the null hypothesis. And what that means is that maybe it's not equal to 0.24, but at this point in time, the sample that I got, which said 27%, was not enough information to say that it's not 0.24, right? Maybe it isn't, but at this time, I can't say that it's not 0.24. Does that make sense? That's kind of a weird way of saying that, right? At this point in time, I can't prove you false. You might be false, but at this point in time, I can't say definitively that that's a wrong answer. So rather than accepting the hypothesis, we fail to reject it, right? Because we can't say that it's wrong technically at this point, right? So restate the decision using simple non-technical terms. So we fail to reject the null hypothesis, which means what? In like layman's terms, what did we just do? Let's say the Mars Candy Company. Mars needs a capital M. The Mars Candy Company is what? The Mars Candy Company is what? What are they claiming? So they is okay to claim that 24% of their M&Ms are blue. That's what we're concluding. Even though I got 27%, 27% is not far enough away from 24% to say that they're technically wrong. Does that make sense? That's what we're doing. And again, this seems silly of an example because we're dealing with M&Ms, but the same thing works for like drug companies, right? Or pharmaceutical companies that are trying to see if a certain drug, or like vaccines, to see if vaccines are working, right? We just went through that whole yucky, disgusting cycle. Like they're testing these people and trying to figure out like, okay, are enough people who got vaccinated not getting sick?
Well, now they have that pill.
Yeah, now they have a pill, so that's kind of like working as well. So now they have to do tests on that. But they're saying, of the people who are vaccinated, are enough of them not getting sick to deem that the vaccine is effective? Does this make sense? Mm-hmm. Are enough of them not getting sick to deem that it's effective? Yeah? So that's kind of how like this hypothesis testing would work. There's people in research and development that are doing this same thing all the time. What are you boys doing? We have like a triangle like series of smiles going on here. And I know if boys are smiling, then that's not a good thing.
I don't know, we just kind of we just look at each other and just start laughing at each other.
Sure. Yeah. Okay. Right. Okay.
So what if it was in the shaded region? Would we have to?
If it was in the shaded region, what would our conclusion look like?
Would still fail to reject, right?
No, if it's in the shaded region, then we would reject the 24%. And we would say, Mars Candy Company, you are wrong by saying 24%. You need to redo your data,
Would this
right?
be the same?
It would be a reject instead. It's fail to reject if it's in the non-shaded region. It's reject if it is in the shaded region. That's always the way that it works. We'll do another example and then you'll get the idea. Okay? All right. So that's kind of how this works. Let's go to...
Are we doing the p-value?
Oh, yes, p-value method. P-value method. Here you go. That's the critical value method. I like that method better because you're just finding a z and you're doing all that good stuff. And that's it. Right? Okay, so here's the deal. Here's the p-value method. Ready? Okay. All right. This is kind of confusing for people to see. All right. Here's the p-value method. Still draw a bell curve. Okay? And I still have my two shaded regions. Okay, here's how the p-value method works. We're going to get the same conclusion, just a different way. Okay? And, I don't know. You decide. You decide, because I think critical value method is better, but some people don't. So you can decide. All right, here's my bell curve, and rather than having z's down here, right? Here we had like our z scale. These were all z values or critical values. Stats kids, are you really confused with the whole critical value thing? Because you get critical values here and critical values in calc.
Yeah.
Like,
Yes.
different critical values, right? Different ones. Okay. So rather than having critical values, we're going to have percentages. Okay, we're going to have percentages, and here's how this works, okay? My level of significance was 5% or 0.05, yeah? 0.05, but I have two shaded regions, which means that the 5% has to be shared between those two shaded regions. So what percent is in those two shaded regions? 2.5%. 2.5% is here and 2.5% is here. Depending on what your significance level is, that's your 2.5%, yeah? Or that's what what's in each one, okay? Now, I make this a scale going from 0 to 100. Here's 0, here's 100% over here, right? This cutoff mark will be at 2.5%. Do you see what I'm doing? The cutoff mark for that shaded region, if I'm like filling it with water, imagine that I'm filling it with water from left to right. Filling it with water from left to right. 0% over here, 100% over here. 2.5% is where it cuts off, right? What will this cutoff mark be? 97.5%. Okay? Are you ready? Here's how this works. Rather than comparing the 0.702 to the 1.96, we are going to go to the chart and we're going to take 0.702 and we're going to say a z value of 0.702 equals what percent? Okay, so go to your normal bell curve chart. You're on the positive side and you are actually looking for 0.70. Okay? Not this one, the other one. I don't know. Yep, I do. Right here. Positive side. You're looking at 0.70. 0.70, and it should be something like 0.7580.
Yeah.
You see that? 0.7580, which means 75.8%. Do you see that? 75.8%. So, if I am filling this with water and I start from the left and I fill to the right, where is my 75% going to land? Right here. The same as it did when I was doing the critical value method. It's just looking at percentages rather than looking at the z values. Does that make sense? Okay? But we're still at the same spot. 75% is going to live here in relationship to the 97.5%, right? 75.8% lives there. Which means we're in the light color, right? We're not in the extreme values, which means we're still going to fail to reject the null hypothesis. Woo! Is this a lot? You guys will get so good at this. We'll do this over and over again, and you'll just be like, "Oh, I know what it is, right? I know how this works." Okay. I don't know that I even want to go through the actual notes. Let's go to your homework assignment. Should we do one of those?
Yeah.
Should we do one of those? Okay. Yes.
How do you look that up again?
Oh, So you look here on the positive chart, you're just looking at the z value of 0.70. So you go to 0.7 and go over to the first column. Do you see that? 0.7580? Yeah? Yeah? Good. Ask. Yep. Oh. Why don't we go to the what? Oh, because of 0.702. So we round to 0. Yep. Good question. Very good question. Ooh, look at all that stuff. Look at all that stuff that we've got going on. All right, let's go to the homework assignment, which looks like this. And let's go down to number 5. And here we are converting to p-value. We're doing the p-value method, the method that we just got done doing. We will do one of these, and then let's go to the other side, and let's do number 7 together, and that's the critical value method. Can we do that? Yeah. So we'll do one p-value, we'll do one critical value, and then you try to do the rest of them on your own and see how that goes, right? Yeah. We'll see how that goes. Okay, here we go. So, number 5, the test statistic. The test statistic, so they're not even having you calculate the test statistic. They're giving that to you. That's exciting. So all of the work is done for you, like the formula that we did to find z, which was p hat, q hat over the square root of p, q over n. That came out to be 1.59. They have done that for you. Thank you. Boom. They've done that for you. That was my test statistic. They've done all that stuff for you. We are trying to claim that P is greater than 0.1, okay? Our null hypothesis always refers to P, and the first one, the null hypothesis, is always equal to. We always start with equal to. So we're going to say that it's equal to 0.1. Now, in the problem that we did before, our alternative hypothesis was P was not equal to 0.1. But in this one, we're saying P is greater than 0.1. Okay? So, rather than using equal to, or rather than using not equal to, or less than, or greater than, this one we're using greater than. Okay? Now, this changes this just a little bit because you are only going to be looking at this right side here. If it's not equal to, you're looking at the two sides. But if it's greater than, you're looking at that side. If it's less than, you're looking at this side. Let me put a little key code over here. Not equal to. Your bell curve is going to be shaded this way. This is what not equal to does. It is called two-tailed. Why would it be called two-tailed? Because it has two tails. Greater than is going to be just the right side. That is called, anyone want to take a guess? One-tailed. And the less than is also one-tailed, but he is on the left side, one-tailed. So we're only looking at the right side tail, and these are actually easier than the not equal to ones, because when I'm doing the p-value method, you don't have to split your percentage. Like the 5% we split to 2.5% and 2.5%. You don't have to do that this time. Don't write that down because we're not even using 2.5%. Okay? All right? We have everything set up, ready to go. Okay? One more thing that I want you to write down is that we are claiming that P is greater than 0.1. So put your claim with the alternative hypothesis, or H1. Your claim will not always go with H1. Sometimes we're claiming that it is equal to. Okay, but this time your claim is going with H1. We'll get to that. You'll get used to that. Identify the hypothesis test as being two-tailed, left-tailed, right-tailed. Which one? We're right-tailed because we're only dealing with greater than. So we are right-tailed. Find the p-value. Okay, so when they're saying find the p-value, they are saying that 1.59 is my z, because they calculated that for us. They want us to find that as a percentage. What is that p-value? Find that as a percentage. So we're looking it up on the chart, and we're on the positive side. So find 1.59 and tell me what percentage that is. 94 point what? 41? 94.41%. Did everybody else find it? Yep. Okay. 1.59, 94.41%. Okay. Use a significance level of 10%. Okay. That means the 10% goes here. If this was two-tailed, we would have to split it and be 5% and 5%, right? but it's just 10%. Okay? There's how that works. All right. So, what? No. We're not doing it. We're just looking at the 1.75 here. So don't look at this box down here. The only time you look at this box down here in the corner is when you're doing the critical value method. So when we're doing the p-value method, you look it up here. Confusing. You'll get used to it. Just wait. I know. It's frustrating. Using a 10% significance level. So let's label our bell curve. If here is 0% and here is 100%, my cutoff mark, there's only one of them, is what? What is this cutoff mark right here? 90%, right? So that means if it is anything larger than 90%, we're gonna be in the shaded region, and shaded means reject, right? Okay, so we are at 94.41%, which is in fact in the shaded region. Yeah? Okay, so if you're in the shaded region, that means it's an extreme value. It's not going to be equal to the average that lives here in the middle because it's on the other side of that threshold, right? The average lives here, 0.01 lives here, and we're saying it's not equal to that. It's way on the other side. It's an extreme value. So we are going to reject the fact. We're going to reject null hypothesis. We're going to reject H naught, which means that P is not equal to 0.1, right? He is on the extreme value. He's not in the middle there. He is on the other side of the threshold that tells me that he's close enough to being 0.01. So we can conclude, conclusion, claim that, is it point, yeah, it's 0.1. Did I put point, no. Oh, shoot, 0.01. Wrong, yes, 0.1, yes, you're right. Conclusion, claim that, that P is greater than 0.1 is correct. We're saying P is not equal to 0.1. It's actually on the other side. It's on the threshold where we can definitively say that it is greater than 0.1. Ooh, this is a lot. Yeah? This is a lot? Okay, why don't we just not do the critical value method until Monday so you can get used to doing this? Try to do number 6. You're doing that same process. I know. I'm looking at your faces and you're like, what? That's because this is the first time and each one of these has like 9 steps to it. Just go through and try to keep your thoughts organized. Just do step by step what we just did. Yeah. So all you have to do is number 6. That's it. Number 6 and be done for the weekend. Okay? Try to do it the same way as what we did. Okay. I'm going to stop the video.